Okay, it's the first lab of the semester and our focus is constant velocity. So before I introduce the experiment, it's important to note the key concepts that the experiment tested. These derive from the two fundamental Newton's laws. The first law is that objects at rest tend to remain at rest and objects at motion tend to remain in motion unless they're acted on by an outside force, meaning that their velocity will remain constant. And the first equation I have listed is derived from Newton's second law, stating that final velocity is equal to initial velocity plus net force divided by mass times the change in time. And this equation shows that if net force is equal to 0, then final velocity is equal to initial velocity, as the first law states. I also have 3 other equations listed that were important during calculations for this experiment, including final position, and velocity and average velocity. So the goal of the experiment was to model Newton's fundamental laws in the real world. So I recorded an orange that I had pushed with my hand as it rolled along the floor, and I used tracker and glow script to both observe and compute the constant velocity of the orange. Some key things to note are the mass of the orange and the total time the velocity was recorded for. It's also important to assume that there was no air resistance or friction acting on the system and that net force was 0. So in this experiment, the system was the orange, the floor, and the earth, and I used tracker to set the axes for the orange's movement, and then I used their motion tracker to plot the observed position of the orange over time. I set the initial position of the orange at the origin, and then this data provided me with the basis to calculate the initial velocity of the orange, for which I used the change in position of the orange from the first to the second frame of the video. And this initial velocity is what I used to set up the code in glow script. So this is the initial section of code for the system properties and initial conditions. The first section asked for the mass of the ball, or orange, which I put in as 0.071 kilograms. Then I used the tracker data to input the initial position and the velocity of the orange. And then I left the initial time as 0 seconds and adjusted the delta t, which is the size of the time step that the program calculated, to be similar to the frame rate in tracker. The next section of code contains the while loop for motion prediction and the visualization. First, I inputted the final stopping time that was used in tracker, which was 2/3 of a second. And then I left the net force vector unchanged because net force in this experiment is assumed to be 0 following Newton's first law, so that final velocity equals initial velocity for each time step. And then last, I updated ball.vel and ball.pos to reflect the equations derived from Newton's second law. Therefore, as the while loop ran, the computational velocity remained constant because there was no change in net force from 0, and the position vector, ball.pos, changes with each increment in time, or each time the loop repeats. Once I ran the code in glow script, I was able to put the observed and computed data into an Excel spreadsheet and create this graph that compares the two. The graph shows position versus time of the orange for the entire length of time. The observed velocity from tracker is shown to decrease relative to the computational data that remains constant. The computed position is changing at a consistently constant rate because there were no changes in the computed net force. Therefore, for each time increment, the final velocity was equal to the initial velocity. However, in the observed data, this did not happen, which suggests that there was some net force acting on the system and causing the orange to slightly decelerate over time. So the answer to the first question, what if question, which was what would happen if the axes were flipped in tracker, is that we know that the velocity vector is made up of the magnitude of velocity times the direction of velocity. And when we change the direction, this means that the overall velocity must change too. However, flipping the axes will only change the direction and not the magnitude. And therefore, the sign of velocity will change, in this case from positive to negative. The second question asked how many pushes and pulls are added together to get net force, and it is impossible to measure or observe those. And while it's impossible to know the net force acting on the orange, we do know that friction and air resistance are acting on the system. Additionally, we cannot precisely measure the pushes and pulls in this particular experiment, which is why we set net force equal to 0 in our calculations and in the computational model in glow script. And to close, it's important to highlight some possible sources of error in this experiment, including friction and the uneven surfaces in the system, which could cause the deceleration of the orange. And the movement of air in the room, also possibly from the AC, could affect the orange if there was a strong draft.